How to me is the algorithm. It'll work. You don't really know why. And the why is like the mathematics that proves that it will work. And I was looking at my email. I literally stopped in the middle of the road and I didn't know whether to shout.
Celebrity dance or something.
Yeah, exactly.
Quite a coincidence or timely that you have written this very authoritative book on AI.
Hopfield networks, while they were amazing for when they were done, are not sort of key to today's AI. Universities have been the places where people don't worry about time frames. They're in it for the long haul. If you look at the way they are trained and the mathematics of it, it's fairly straightforward. And yet these systems started displaying a breadth of abilities. And that's the thing that opened people's minds to the idea that, oh, maybe we are very close to this thing that they've been calling artificial general intelligence.
We will all end up being users of AI. There's no question about it. This is something one would live with for decades.
These artificial neurons are extremely simplistic models of what a biological neuron is. In the prologue itself, I say this is not bedtime reading. You have to persist with it.
Anil, welcome to SparX.
Thank you very much, Mukesh.
Yeah,
My pleasure.
I've gone through both of your books, or two of many books, I guess, you've written around science and physics. And the latest one in Why Machines Learn could not have been more timely. I think we can say 23 and 24 both have been year of AI. This morning, I was in an event with Satya Nadella. So he's here, talking about AI and all the things that are going to happen in the coming years. So it's quite a coincidence or timely that you have written this very authoritative book on AI. There are a lot of books hyping what AI can do and all of that, but this is a book that really goes into the heart of AI, and very brave book, I must say as well, because you have tried to translate a lot of complicated computer science, math stuff in reasonably accessible manner. I think anyone who knows high school math should be able to follow along most of it. So just what was the thought process behind writing this book?
Well, it began quite innocently. I had no idea that AI was going to blow up the way it did. So I think my story about how I got interested begins in 2019 when I went to MIT as a Knight Science Journalism Fellow. And for that fellowship, you have to do projects. So I had proposed that I would actually go back to teaching myself deep learning and, go back to my software days, literally start training myself again to understand this technology. So when I was there as a project, I just learned how to code again after 20 years, sitting in classes with the teenagers at MIT. It was quite intense.
And you're learning Python this time?
I learned Python this time because the last time I coded was in Java. That was probably in the 1990s.
Right. Well, something common between us, the only programming language I properly learned was in Java in late 90s, and yes. I did work as a Java programmer for a few years.
Yes, so Java was the last. Most of my programming was in C and C++, and then the final programming language that I did was Java. So there was a 20-year gap. It was actually fun to do Python because I think it's a lovely language. And but so during the MIT thing, I just did a project. It was mainly coding, and I kind of understood some of the conceptual ideas, but it was still unsatisfactory. And then the pandemic happened. And I got stuck in the US for many months, by myself. And by then I had gotten interested in wanting to learn more and more about machine learning. So I just started doing just watching endless amounts of lectures. And at some point, I got fascinated by the math. Because, once you start kind of getting under the mathematical skin of this whole field, it's actually quite beautiful. And like you said, it's relatively simple. At least the basic concepts are not very difficult to explain. So that combination of, the storyteller in me encountering this, and then, being able to appreciate the beauty of the math, all of that somehow finally came together. And I felt like, okay, there's a book here that I really want to communicate these ideas to people, but not in the standard sort of not just tell a straight nonfiction narrative. I wanted to get into the math.
Yeah. I think this is, just not saying this just to please you, Anil. I think this is destined to become one of the, key book, seminal book in this area, because there's so much interest around AI, and not everyone is going to study computer science or take calculus courses but this is, one way for people to get fairly close to what's going on inside the black box. And we'll talk about that a lot more. In fact, I see on the cover page, Jeffrey Hinton says masterpiece. That must be quite, coming from him, quite an endorsement.
It was. I mean, I still remember I had, so I teach journalism here in Bangalore at NCBS. So I had just finished my workshop, which is a 2-week-long workshop. And the students and we were walking through the campus going for our final dinner.
Mm-hmm.
And I was looking at my email and I see Hinton's email where he said what he said. So I literally stopped in the middle of the road and I didn't know whether to shout.
Celebrity dance or something?
Yeah, exactly. But I was, I was an instructor. All my students were there. So I had to pretend to be relatively unfazed. But it was an amazing.
What did he say more about the book? Did he read the book?
Yeah. I mean, there are 2 chapters that deal with his work also in the book, right? Backpropagation and AlexNet.
Yeah.
So the book was sent to him and he read it and responded.
Amazing.
So, I was taken aback.
Yeah, I'm also curious about the title, Why Machines Learn. I would have thought the book is about how machines learn. Why almost implies a motive. There is something they're trying to do. There is a reason. Or what was the thought process? You must have thought about why versus how. And what the choice of why?
How to me is the algorithm. Just, if you just write a piece of code, the sequence of steps, right? So, for instance, if you take, the first artificial neural networks that are described in the first 2 chapters, the perceptron algorithm. So, there's, it's a very simple algorithm. You can write it in 5 steps. So, that to me is the how. Mm-hmm. And it'll work. You don't really know why, right? And the why is like the mathematics that proves that it will work. Mm-hmm. So, to me, why here is just the mathematical rationale for why algorithms do what they do, right? Why does the algorithm behave the way it does? Why does a machine learn?
Got it. Maybe you are getting to the heart of the... We expect algorithms to be very predictable. They're, coded to do something and they repeatedly at scale do. That's how most software engineering has been. Yeah. But something happens in these particular algorithms that you have described in a lot of detail that they're actually able to learn from data and keep getting better. So I think this, I guess, the why is addressing why they are able to.
Yeah, exactly. And like, for instance, there are algorithms where, for instance, the same algorithm will work when you're dealing with low-dimensional data. Mm-hmm. And when you move into higher dimensions, the same algorithm doesn't work. And if you just looked at the algorithm, there's no way of telling why it won't work, right? So the why is really about understanding the mathematical rationale.
Got it. And throughout the book, I think you cover a lot of history of how AI has evolved. I guess one can almost say maybe either AI started in 1956 with the Dartmouth conference, or maybe started with the Alan Turing's paper. How do you look at it? AI has its own ups and downs, and what is your perspective? When do you think AI really started to come of age? Not necessarily in the mainstream media, but in terms of really demonstrating that there is something real here, which we extrapolate in the future. It's very powerful. When we start to become something from a very esoteric academic project to something with the possible profound implications for the world.
The thing is that if you look at the narratives that were there at each phase of this process, I seriously think that the people who were doing it believed that the breakthroughs were imminent. I mean, if you look at the Dartmouth manifesto, when they coined the phrase and had the first artificial intelligence conference, they were talking of solving it in a few months, right?
Summer project.
So, summer project. It was like it was going to be done, if a few bright minds got together, it would be done in a few.
We still do startups like that in Bangalore.
Yes. Yes. So I think to be, and to be fair to them, I think they probably saw it like that and they didn't realize just how difficult a problem it was. And so at each of these phases of the development of AI, there was excitement that the solution was just around the corner, which also is the reason why they kept going, right? Because if you think that it's too far away, like for instance, there's a chapter in the book about Bernie Widrow, so Widrow-Hoff least mean square algorithm. I mean, he went to that conference in the 1950s. He was a student at MIT. He goes there and then comes back all fired up, wanting to build thinking machines. and very literally almost immediately realizes that I don't think it's going to happen in 25 to 30 years, so decides to drop the idea, right? So here was someone who got excited, but also immediately realized that, okay, this is not around the corner, right? But most people were not like that. I think they, whatever they were working on, they were so convinced that the breakthroughs were imminent.
Yeah, and very quickly from that conference, we have this perceptron, which is probably very first demonstration of a primitive neural network which is able to learn. Was that seen as a big deal at the time?
Yes, the perceptron was a very, very big deal because, prior to the perceptron, we had the McCulloch-Pitts artificial neuron, right? That was the first computational model of the human neuron. But that was just a neuron that could compute. It was not a neuron that could learn from data, right? So the first artificial neuron was the perceptron, and it was a single layer neural network. So the algorithm worked only if you had a single layer. But it really was the first formidable demonstration of a neuron, artificial neuron that could learn from data. But more importantly, I think the real reason why it was such a big deal goes again back to the heart of this book. There were mathematical proofs. So, Frank Rosenblatt comes up with the perceptron algorithm. He builds the machine. All of that happens in the late 50s. And by the early 60s, people start proving mathematically that this algorithm, if a solution exists, it will find it in finite time, right? So it was setting a lower bound for it was a computational complexity problem that was solved. So suddenly an algorithm which was, doing something, there was a mathematical rationale for why it worked and why it will always work if a solution exists. That was, like I say in the book, it was like gold dust, like, being able to do that. And so, yeah, it was a very big deal. And Frank Rosenblatt also, he wrote this huge book in the early 60s called The Principles of Neurodynamics. There was a lot of back and forth between ideas in neurobiology and what these guys were doing. So, yeah, it was a big deal.
Right. And maybe, one thing worth, repeating here for the audience listening is, we're talking about late 50s, early 60s, which is what, 70 years roughly. Most of us were not born. So people were talking about artificial intelligence seriously. And with this perceptron, there is this real demonstration of this thing could learn to recognize characters fairly quickly. And I think it was quite broadly covered in media as well, with the, probably very outlandish headlines about what might be possible in few years. Yeah. But it was real stuff. And as you say, with very comprehensive mathematical proofs as well. So it was, not pipe dream or some fringe.
No, it was not fringe at all. Absolutely. And in fact, when, one of the reasons why the research into artificial neural networks kind of died, ironically, was because of a book called The Perceptron. And that was a book written by Minsky and Papert, Marvin Minsky and Seymour Papert of MIT. And in that book, they basically proved mathematically that the single layer neural network, the kind that you could build with the perceptron, would not be able to solve some very, very simple kinds of problems. So the perceptron was what would be called a linear classifier. It could find, like if you had to classify two kinds of data, as long as a divide existed between those two kinds of data, it could find, a linear line or hyperplane. If there was a separation that was nonlinear, it couldn't do it. And that book then basically proved that it couldn't. And then they kind of insinuated that multi-layer neural networks will also not be able to do such complex problems. They didn't prove it. There was no mathematical proof. It was just kind of by insinuation. And there was some sociology going on because Minsky was more interested in a different kind of AI, symbolic AI. And this was connectionism. And so I think, usual issues of funding, etc., must have been there. I don't know the details there. But
there is this perception of because, and maybe you also mentioned that, now definitely, Jeff Hinton is godfather of AI, broadly accepted. But before that, Marvin Minsky was the godfather of AI and was, very renowned computer scientist and so on. And because of this particular book and the whole field at the time shifted behind expert systems and huge amount of investment did happen in 70s and 80s and so on. Is there also sense that in some ways this connectionist approach or neural network approach or some ways got held back as a result of those choices, or it just wouldn't have happened regardless?
Some things got held up, I'm pretty sure, because the breakthroughs that happened, if you look at the kind of breakthroughs that were needed, one was the training algorithm that was needed to figure out how to train multi-layer perceptrons, right, or multi-layer neural networks. So that happened in the mid-80s. And that was basically Hinton, Rumelhart, and Williams, their Nature paper in 1986. But there was plenty of work predating that was already hinting at the algorithm that was necessary. Even Rosenblatt in early 1960s, in his book Principles of Neurodynamics, he talks about the backpropagation idea, right? But nobody picked it up, and part of it was because nobody really thought that multi-layer neural networks would work, except a few people who kept the faith, including Hinton. Like Hinton, by late 60s, was convinced that neural networks will be important. He didn't know how to train them, the multi-layer ones, but he kept at it. And so there were very, very few people working. Now you can imagine that if the funding hadn't shifted to symbolic AI and expert systems, etc., more people would have been working on connectionism, and at least backpropagation would have been figured out earlier. And there were other mathematical results, like being able to prove that a deep neural network is a universal function approximator, right? Or the kind of artificial neurons that you were modeling. Those things all could have happened faster because they were not dependent on compute power or data. They were just conceptual ideas. I think they could have been speeded up. But then the second phase of this development, which is when deep neural networks really became important, that had to wait for a compute. Like, we didn't have GPUs. I was just listening to Jensen at his talk at, I think, the CES conference just now, yesterday. And he was giving a history of the GPU development. And so it was late 1990s. And so training multi-layer neural networks, deep neural networks, wouldn't have been possible without GPUs. So that had to happen. So that was one obvious sticking point. The other was the amount of immense data you need to train these networks. That, again, would not have been possible early on before the internet, because really the data was made possible by the internet. So I think you can look at it in two phases. One that was conceptual, which would have happened earlier, and the other was technological, which just had to wait for its time.
Right. And I know you interviewed Hinton pretty extensively for this book. But what was his motivation during, I would say, mostly 70s, 80s, when I don't think this area was getting any attention? How was he able to sustain energy? Were there other researchers around the world who were tinkering with this whole connectionist approach? Just to paint the picture of, what was the neural network landscape in 70s, 80s, early 90s until the...
There were very, very few people. And he was in Britain. And he was pretty much the lone person in Britain. He was regarded as slightly, doing the wrong thing, basically. So you have to credit his persistence here, because through the 70s in Britain, he persisted when he had no support. And he moved to the US partly because I think I have that anecdote in the book where he talks about saying, in Britain, if you were wrong, you were an outcast, and it was a small community, and he was an outcast in that sense. In the US, he felt like, at least there are two coasts, like, you can be an outcast on one coast, but on the other coast, you might be accepted. And that's how it happened. He moved to San Diego, where there was work happening in connectionism. But through the 60s and 70s, I think he was pretty much by himself. There were not that many people. And to your point, the only other big name that picked up on connectionism towards the end of 70s and early 80s was John Hopfield. And it's no coincidence that John Hopfield and Hinton won the Nobel this year for physics, which was slightly debated as to whether that was the right thing or not. But there are heavy physics principles that, inform their work. So, I'm okay with that Nobel. It's not for me to decide anyway. But there's a very easy case to make about their physics sort of roots. But I think the real reason why Hinton persisted was, and this is a story that gets lost when one is talking about AI. A lot of the AI researchers, especially in the early decades of it, were building AI as a way to understand the human brain. So they were much more interested in understanding how the brain works. And they kind of took the Feynman way of thinking about this. Like, if I can build it, I will understand it. So they said, okay, let's reverse engineer things to the extent possible. And so connectionism, it's very, very clear that our brain is a neural network. So that's where the term comes from. So, by trying to build simplistic models of it, those were the first steps.
Right. Got it. And since you mentioned John Hopfield, who is one of the Nobel Prize winner this year, and I think his background was condensed matter physics.
Yeah.
A lot of physicists, take almost claiming now that in some ways the research in physics gave birth to, very early ideas around neural networks. So for our listeners, can you help explain what was Hopfield's contribution, the so-called Hopfield network? Why is that relevant for, what eventually happened with neural networks?
So, yeah, like you said, Hopfield was a condensed matter physicist, and he had done some very seminal work in solid-state physics, condensed matter physics. And then at some point, he felt kind of like he had done all that he could do in that field, and he was looking for new things to do. And in the beginning, he did a lot of work in actually biochemistry of all things, but the dynamics of biochemical reactions. So while he was doing that, he realized that there were principles that he had uncovered about how these biochemical reactions proceed, the dynamics of them, how they do error correction, that he could potentially apply that to try and understand how the brain might do associative memory, right? And associative memory simply being this idea that if there's a memory stored in the brain, then you can retrieve that using some fragment of that information. And like, for instance, you might have a strong experience that involves, wonderful smells and flavors of food or whatever. And then many days later or months later or years later, just a fragment of that smell can, bring back that entire episode in your memory. And that would be associative memory. And he realized that you can build neural networks that could store a memory. And then if you corrupted that memory by just corrupting the outputs of neurons. So let's say you had 100 neurons and the output of each neuron was the value for a pixel. So 100 neurons would be a 10 by 10 image. So literally you can store, let's say, in the outputs of those neurons, a 10 by 10 image. So, and he realized that if you design your network such that when the memory is stored, the network is at its lowest energy state. So the way he designed the network, he basically figured out that by storing a memory such that the stored memory represents the lowest energy state of the network, anytime you corrupt the memory, the corruption essentially moves the energy state of the network to a higher level. And the dynamics of the network are such that it will automatically find its way back to the lowest energy state. You don't even have to do anything particular. It's just the nature of the design of the network is such that the moment you corrupt it, it's an unstable network. The dynamics will take it back to a stable state, which is an energy minimum. And if your corruption was such that, you can imagine, just as a metaphor, your energy state is your energy landscape is some sort of convex bowl, right? Concave in this case, but the function is called convex. So your energy minimum is at the bottom of the bowl, right? That's where, if your network is at that place, it represents the stored memory. And if you corrupt the network, it ends up somewhere higher up in that energy landscape. And the way he had designed the network, the dynamics would just automatically take it back to the bottom, and you could retrieve the memory. And that was his essential contribution. And the way he designed the network, the ideas come from solid-state physics. So there's this icing model of electromagnetic materials. So this is something that you see in ferromagnetism. So he basically used those models to design the neural networks. To tell our listeners more clearly, I think the work that he did is not the kind of stuff that is happening in deep learning today, right? So what he designed would be called a recurrent neural network, where these networks are the neurons are dynamically affecting each other, right? So the output of one neuron goes to another neuron, and the output of the same neuron can come back to itself. So there's inherent dynamics. Today's neural networks are all what are called feed-forward networks. The information comes in, and the computation just proceeds in one way and then exits on the other side, right? So right now, we don't have recurrent neural networks of the scale that we are seeing with the feed-forward networks. So Hopfield networks, while they were amazing for when they were done, are not sort of key to today's AI. They will probably become key eventually because recurrence will be important as we go forward.
Got it. When we'll definitely talk about where this whole thing is headed. But other big breakthrough, which you briefly alluded to, is this whole backpropagation. That is somewhere in the book you call it's the workhorse of what's happening with AI today. So what's the easiest way for our listeners to understand what is backpropagation? Why is that so seminal and important for everything we see with AI around us?
So backpropagation. Okay, let's talk about what a network has to do. A neural network is simply layers of artificial neurons that are connected to one another. And any given artificial neuron is simply a unit of computation. Inputs come in, it does some computation, produces an output, and that output is then connected to the inputs of other neurons. Now, if you have layers of these neurons connected such that the inputs are coming in from one direction, the layer of neurons do some computation, feed their outputs to the next layer, and those neurons then do that computation, feed their outputs to the next layer, and so on until you come to the output side. Now, when you do something called supervised learning, let's say you're trying to recognize images of cats and images of dogs, right? So again, we can take a 10 by 10 image. So you have 100 pixels. So on the input side, all the 100 pixels are coming in. On the output side, you just simply want an answer saying -1 or +1, saying it's a cat or a dog. And some human has, or bunch of humans have labeled, let's say, 100,000 images as being either cats or dogs. So you feed the network the pixels. On the output side, it will produce a -1 or a +1. And in the beginning, it will be wrong because it has no idea. You're training it. So it will produce, say, let's say -1 instead of +1. But as your algorithm knows that, okay, the answer should be +1. So it can calculate the error that the network makes. So you have a value for the error on the output side. Now, backpropagation is simply this idea that when you make an error on the output side, you have to figure out what is the responsibility of each of the connections that exist in the neural network. And these connections are all denoted by weights or parameters. So what is the credit to be assigned to each of these parameters in terms of how much they have contributed to the error? And historically, when we had single layer neural networks, the output was literally just right next to the layer of neurons. So you could figure out what that assignment was. But the moment you had multiple layers, you could figure out what how much credit to assign to the output layer. But it took 20 plus years to figure out how to propagate that error back through the layers, right? And it actually turns out a very simple rule in calculus called chain rule that you can use. But the essential idea there is that you calculate the error on the output side and you start assigning blame to, the parameters of the first layer, and then you work your way backwards, propagate the error back all the way to the input side, and hence the name backpropagation.
And this is the paper that Hinton published in Nature in 90s.
80s. So it was a 1986 paper by Rumelhart, Hinton, and Williams. And again, to be fair, this idea, even though Hinton now these days gets all the credit for that, even he will say that, they kind of made it work for neural networks. The essential idea of what backpropagation is, the idea that there's an error that a system is making and there are multiple layers of computation going on, and you have to somehow figure out how to propagate that error back all the way through the layers of computation, that had been around, right? In fact, people who were doing rocketry and control systems for rockets in the 60s, they knew this, because when you launch a rocket, you have some model of how your system is going to sort of do the navigation, and you have a calculated trajectory, right? The rocket is launched and it's moving through space, and at every point you have to look at where the rocket is relative to what your model is saying. And so for every time step, you have to kind of backpropagate the error that your model has made relative to where the rocket actually is, right? So the ideas of backpropagation were already there in various forms in control systems, in economics, and all sorts of other places. So Hinton's paper with Rumelhart and Williams was seminal in the sense that it kind of brought all these things together. And it also showed not just that you could train a neural network using this, but they actually showed that when you train a neural network using backprop, it actually learns features about the data, right? If you're looking at images of dogs and cats, maybe it's learning something about what makes a cat and what makes a dog, right? And those representations that it learns, they kind of highlighted that aspect.
And from what I understand, so from there onwards, slowly people started using backpropagation for building these multi-layer neural networks and applying things like recommendation systems and classification and so on. And then big win happened, I think, 2012, when again Hinton's group ended up winning this ImageNet competition. Something was people were not anticipating that to happen, and suddenly kind of caught everyone's eye and started accelerating a lot of interest and investment in that area.
Yes, I think I think you picked up on the right sort of inflection point when it comes to deep neural networks, because until then, and so they were solving a problem in computer vision, which is basically image recognition. And until that breakthrough happened, a lot of people in the computer vision community did not think that neural networks would crack this problem, right? Because they were working with other traditional forms of computer vision, which hadn't succeeded, by the way. I mean, they were good, but they were not scaling up, right? But they were still state of the art, these non-connectionist, non-neural network approaches. And they were very, very well-known people who were convinced that neural networks would never be able to crack the image recognition problem. So I think it was 2009 or so that Ilya Sutskever, Alice Krzyzewski, and Hinton, they were Hinton students. They started working on this problem. Alex was the whiz kid at coding GPUs, and Hinton was the advisor, and Ilya was the guy who saw the promise. He was the guy who convinced Hinton that, look, I think we can crack this ImageNet problem. ImageNet was just a competition that had been set up by Feifei Li and her team, where they had, I think, millions of images that had been annotated, and it was an annual competition to see what software does best. So I think that was a huge moment, because suddenly it was clear that you could crack this problem using deep neural networks, and also you had a thing that could scale, right? So investment started happening.
And around same time frame, I think perhaps even a little earlier, DeepMind was founded, and these guys, with the ambition of solving intelligence as their purpose. And Dennis Hasabi is the other chemistry AI Nobel Prize winner this year for the work that they have done with the protein folding problem, which is, the way it's communicated is that it used to take one PhD to solve one protein, and now we have solved hundreds of millions of proteins, which is again another seminal outcome and shows the potential of what these things can do. But as you were researching this book and thinking about, what would give someone in the first decade of the century, even the courage and the belief that this is something, worth investing in, and this, will be able to solve big problems on 5, 10, 15 year time frame, which they eventually did. Some insight on that,
I think you have to think about this from the perspective of researchers, scientists, and academic. This was not happening in the industry, right? I think that is crucial too. Like John Hopfield was not doing this as an industrial thing or a business thing. He was after, some very sort of, deep questions that he wanted to answer about the nature of the brain. And in this case, a very particular problem of how to solve the problem of associative memory, right? So these are all curious people, and curiosity drives them far more than anything else. And again, much of Hinton's work, today we know Hinton as the godfather of AI, but he did his work in relative obscurity for a long time. as a scientist, as a researcher. So, I haven't kept up with Demis Hassabis's career and work. He probably is more on the industry side now, but even he is a scientist first and foremost. I think to me, that's the way to look at these developments, right? A lot of these people, to them, 10, 15-year time spans are nothing because they are invested in it for the long haul, and they're doing it out of scientific curiosity. And then these breakthroughs happen which have industrial applications, and then, everything becomes very different. But I think if you're a person in the industry saying, I'm going to put 15 years into something where you don't see immediate payoff, I don't think that's an easy thing to do, right? It completely works. It works differently in academia.
So that's a very significant point, because now, with so much interest in AI, a lot of people asking this question, including in India, how do we catch up? How do we play some meaningful role in this, AI revolution? It's unfolding. But one has to recognize that there is this whole long-range research component to this. And that whole ecosystem also needs to be nurtured and developed parallelly. You can't just commit at the fag end and hope to become a player in that area.
I would agree. I think this is about the basics. So this is really making a case for blue sky research, right? I mean, even DeepMind or Google Brain, they were shops for blue sky research. It wasn't clear what the immediate payoff would be, right? Of course, Google was, had an income stream that didn't depend on that, but it was willing to invest in just research with no obvious payoff, right? And somewhere there is a belief, right, that it will pay off probably. But I'm sure there's a lot of research that goes on in these companies that go nowhere. And so we only see the end result of the good ones. There are probably other things that are just, left by the wayside. But the stuff that's happening in institutions, in research institutions, that is the long horizon stuff. And they are doing it, I think, a lot of it. Things have changed now with the strong confluence of industry and money and, and research. So the dynamics are different now, both in AI and, of course, it's been like that for a while with biotech, right? So I think those dynamics are changing. But in general, I think universities have been the places where people don't worry about time frames. They're in it for the long haul.
Yeah, and then the course of researching your book, and you mentioned a lot of these stories, you did talk to a lot of these people who are in the academic environment, working on something in all the way back to 60s, 70s, 80s, and so on, in relative obscurity. And in some ways, they laid the foundation of what was to eventually come. So it's worth acknowledging their contribution, patience, and almost like selfless commitment to just serving this curiosity without really knowing where it is going to lead them.
Yeah, I'm not sure about the word selfless. I mean, they, for them, satisfying their curiosity is their thing. So, but I know what you mean. I mean, in a sense, the payoff is not obvious, right? And they're doing it purely for the love of sort of solving a problem, and that itself is,
or for the H index in the
yes, possibly. That's why I didn't want to go to the selfless part, because the academics can also have inflated egos, but so that's a different story.
It's a different currency, I guess.
Yes. Yeah.
Right. I think the reason I'm asking you about that is, again, just putting the India hat on, is somewhere, AI is obviously here to stay, and it's going to go through its own evolution. It's also not like we are done. Internet was there in early 90s. Internet is there today. It's very different.
Yeah.
Right. And so AI is going to go its own evolution. And for whatever roadmap and path we figure out for India, how we're participating in that research, nurturing each ecosystem, and having at least somebody working on 5 years from now, 10 years from now. Otherwise, in a 1 or 2 year time frame, this catching up is just not feasible.
I would agree. I really think we need research labs that have that kind of time frame to play with, where they're not under immediate pressure to produce applied research and applied work. It should be, like when you think of something like the transformer architecture, I mean, that's the thing that completely changed everything. But that just, when you look at it, it was just an academic paper that came out in 2017 or so. attention is all you need. It seemed innocuous, and then everything blew open. There should be labs that should be thinking about these things from the ground up. And you never know what the big innovation will be. Right? But it won't happen if there's pressure to kind of participate in the industry immediately. Right. Eventually, everything will need a payoff, but somewhere blue sky research should be its own payoff, and that's the key.
Yeah. This transformer paper you mentioned, so that came out of this team at Google around the same time, maybe a couple of years later after OpenAI was founded. And then, I guess 2022 is the, with the GPT-2 is when, this kind of start hitting the mainstream. Do you think, by 2015, all the ingredients as far as research is concerned was more almost in place, or 2017 transformer, and beyond that it was just a matter of enough data, some entrepreneurial spirit, and also massive amount of computer resource, just put it together and get the whole industrial machinery turning around this? Or I think breakthrough were needed?
I think the major breakthroughs were probably in place by 2017, right? And then after that, it's been incremental. And I think most of the effort after that has been in the engineering side. Because these are, when you look at the scale of these systems, it's one thing to do a bit of coding on your laptop and then turn it into something that is of the scale that we are seeing now. They're totally different. We're talking of companies building their own power plants next to their server farms. So that is that scale of stuff. So the engineering challenges, I wouldn't even know where to begin. I don't understand the engineering challenges, but they are immense. But I think you're right. I think the fundamental ideas were already in place, and they had to be put together and then turned into something that could be scaled up for these massive systems.
And since you talk to a lot of people who are very deeply involved in what's happening in AI, were you also able to develop a perspective on where are we going from here? What's next? What are the likely breakthroughs in coming years that are, or at least the big problems that people are still worrying about?
I mean, the big question right now. So one of the things you talked of, that inflection point of 2022 and GPT-2 and GPT-3, the real kind of thing that made people sit up and take notice was ChatGPT. That's and that was, I think, GPT 3.5, right? And one of the things that surprised everyone, including people in academia and in the industry, was the breadth of abilities that ChatGPT or LLMs displayed, other LLMs also, not just GPT 3.5, given that they were all trained in a very similar manner. And the training, if you look at the way they are trained and the mathematics of it, it's fairly straightforward. There's nothing esoteric about it. And yet, these systems started displaying a breadth of abilities. Yes, they make mistakes. Yes, they hallucinate. All those things are true. But they were also displaying properties in terms of the way they behaved in responses to questions and queries in natural language that could not have been predicted by just looking at the way they were trained, right? Scaling alone got them that behavior. And that suddenly opened up this question, because until then, the AIs that we had, there were some with superhuman abilities like, AlphaGo and the chess playing AIs, etc., that were much better than humans, but they were very narrow. They were trained for one thing and they did that thing really well. Now, here was something that was trained in a very innocuous way, but it had huge amounts of data taken from the internet, and it had massive size in terms of the number of parameters, the number of neurons. And suddenly it had this capability that was very broad, not deep, but very broad. And that's the thing that opened people's minds to the idea that, maybe we are very close to this thing that they've been calling artificial general intelligence. Nobody can define what AGI really is properly. Everyone has their own take on what that is. So in the last year or two, the buzz around, AGI is around the corner has really become big. In fact, just yesterday or day before, Sam Altman had a blog post or something where he's hinting that OpenAI is very close to something like that. I would take all that with a huge grain of salt. But I think the excitement is there. Saying that, there are enough and more skeptics about whether LLMs as they're currently architected will get us there. Because they are missing some very key components. Like we talked of Hopfield networks and recurrence, right?
Yeah.
The idea that neurons can, like one layer of neurons, right now, the way they are built, if you have one layer, like layer 1, and it provides an output to layer 2, then layer 1 doesn't influence itself, or layer 2 doesn't influence layer 1. The influence keeps moving in one direction. Recurrence means you need connections that go, that feed back. And so Hopfield networks have those, but they're very small.
Yeah.
Whereas, LLMs are huge in comparison. And there is this sense that we need recurrence in the systems so that these systems are able to, one of the things that we think is missing in current AIs is the ability to model the world outside in very sophisticated ways. They certainly are able to represent information about the world, but these models are currently very brittle. And so there is a sense that we need AIs just like our brains. Like our brains, you can close your eyes and think about some task that you want to do and go through in your mind the various scenarios of how you would accomplish that task. And when you ask yourself, how is that happening? That's because your brain has a full internal model of the world that you're trying to think about and yourself in that world, the agent. AIs at this point are not at that stage. So I think whatever breakthroughs will come will have to take this into account, where we need AIs that are going to do such modeling. And some of it will be recurrence. We are seeing elements of that already in the kind of things that OpenAI produced 2 months ago with the O series of models.
Yeah.
And so there is recurrence, but in kind of a tacked on external way. So there's the LLM, and there's an external computation that is kind of building in some sort of recurrence. It's very slow because of that. So the ideal recurrence you want should be within the LLM, and it should be able, the neuron should be able to do at that level of granularity. We don't have that. Right now, the recurrence is at the level of external computation. So people are, I think one should point out that while we know how to build recurrent neural networks, using backpropagation to train them is very slow. The reason why recurrent neural networks haven't taken off is even a small one is very, very hard to train in terms of the time it takes and the computation it takes. So if there is a breakthrough that allows us to train recurrent neural networks as fast as we train feed-forward networks, things will change.
Got it. So the few different things you're saying. On one hand, we are saying that these LLMs have this, so-called emergent, behavior that when people are training and just scaling the number of neurons and the data and so on, people are not expecting it to suddenly start doing things that it started doing, which, pretty much caught everyone, including the people probably who were working on it, by surprise. And is it fair to say this whole area of explainability is now a cutting-edge research area, because people are trying to really figure out, okay, what is going on inside this, we know how we built it, but we don't know how it's producing what is, you can pretend it to, be a tutor or be a friend or someone and have a conversation, and, it will have even emotional response and so on. And we don't fully understand, or even the, all the hallucination, it's people keep saying, hallucination is a feature, not a bug, because it's a very fundamental part of how it is architected. So there is one, that aspect. Second is what you're saying is there are probably hitting some scaling limitations. It is not a matter of, if we scale the current architecture by 10x, we get, exponentially better intelligence out of it. That requires some, different architectural breakthroughs, which may or may not be on the horizon.
So, so you talked of the idea of scaling the existing architecture. So there were neural scaling laws that were empirically figured out in just 2-3 years ago, 2021, not that far back, right? And the idea was that if you keep scaling, then these networks will keep getting better, and the curve follows a power law. So, the general idea was that, we're going to get more and more emergent properties. We should take the word emergent, in scare quotes, because it seems to imply something magical. It's not. The only reason why it seems emergent is because, we build systems that are, let's say, with 10 billion parameters. And the next system that we build is the 100 billion parameters, like a order of magnitude difference. And suddenly this shows properties which the 10 billion parameter model didn't. And it's a step jump in abilities. but no one built the intermediate stages. So if you had built the intermediate ones, you would have probably seen a gradual emergence of properties, not this sudden step change.
Yeah.
So the emergence always makes one feel like something magical is happening. It's not magic. Saying that, we don't fully understand the internal behavior of the systems, right? And so there are people who are working on what are called effective theories to explain, to mathematically model what's happening inside the LLMs.
Yeah.
And those efforts are ongoing to explain their behavior. And we still, bits and pieces are happening, but really explainability is a big issue, right? Not just with LLMs, with any kind of deep neural network, where all you have are a bunch of parameters like, the weights of these neural networks. And you can write down one very complicated function, which is a function of all the parameters to explain how an input becomes an output. But that function means nothing. And explainability is a big area of research. And people are right now trying to explain very, very small, like 1-layer transformers, 2-layer transformers, not these, 500 billion parameter models.
We're in pretty wild situation here. On one hand, these models are able to do things that do seem magical. We also don't, fully understand how exactly are they able to do, even though we understand how they were trained and so on. And there are these possible breakthroughs in short term or longer term, which can potentially exponentially increase what these models are able to do, which will have profound impact on how we live and how we work and so on. So that is all the promise and possible perils of AI and so on. But now to change gear and go back a little bit to the math, how we start the book. And I was deliberately keeping that towards the end of this to not scare people away from the math. But I think that's a very important part. What distinguishes your book is you've really tried to put in a lot of effort to say, look, there is no magic here. It's simple math at some level, at least conceptually, which is scaled to these billions of parameters, and that's how these models are able to do. So let's keeping it as simple as possible. But let's talk about what is the essential math that goes into designing these neural networks.
So I think there are 3, maybe 4 fields of math that you really need, and this is fairly basic stuff. I would imagine, at least in India, high school level. In the US, high school is not as good. So in the US, you would say first year undergraduate, but in India, by the end of high school, most people would know this kind of math. And so
anyone who's ever prepared for JEE will know all this math really well.
Yeah, absolutely. In fact, JEE math is way more than you need to understand this.
There you go.
So you and I have done that, so we know, right? So you need linear algebra. So basically, a kind of understanding of what vectors are, what matrices are, what are the manipulations of vectors and matrices, what they look like. So that you need. You need basic calculus. You don't need very fancy calculus. You need a decent understanding of differential calculus. I would say you don't even need integral calculus at this stage, right? So basic differential calculus. The linear algebra is very important. Calculus also important, but less so. I think the really other fundamental thing is probability and statistics. The understanding that all of this stuff that the machines are learning is based on data that has been sampled from some underlying distribution. And what machine learning systems are trying to do is do their best to estimate what that distribution is. Because once you learn that distribution, you can use that knowledge then to tell apart, cats from dogs, or you can generate new images of cats and dogs. But you need to figure out or estimate what the probability distribution is. So you need elements of probability and element of statistics, probability theory and statistics. So these are to me, the fundamental ideas. There's optimization theory, but that you can subsume for the purposes of this into calculus.
Yeah. Let's also put some effort to explain, how to visualize these neural networks. Because see, when we interact with the GPT interface and ask it to write a poem or tell a joke, it feels absolutely mind blowing. But when you look under the hood, basically just numbers. The each network has some numbers which is learned through all the training and so on. Connections again, weights and biases, again some numbers.
Yeah.
So just help people visualize that, if you can just go inside these things and go, traverse from node to node, what will you see and how it is working?
Yeah, I think you're absolutely correct that when you actually zoom down and go into under the hood, it's literally just numbers. So the best way for me to think about this is think of your AI as a black box, right? On the input side, you have information coming in. We end up representing all information as vectors. A vector is just a sequence of numbers. So let's say you're dealing, again, we can go back to our example of image recognition. Let's say you have a 10 by 10 pixel by 10 pixel image. You turn that into a vector that is 100 elements long, right? So a vector comes in and there's some black box. And on the output side, you have just one number that is coming out. In this case, we just want to classify this image as cat or a dog. So we want one number on the output side, -1 or +1. That is also a vector, but with one element. So mathematically, what's happening? You have a vector coming in. There's something in the middle that transforms that vector, which is 100 elements long, into another vector that's 1 element long. And if you look inside that black box, it turns out to be a matrix. So it's essentially a matrix multiplying a vector. I mean, this is doing it very simplistically, right? So you have a matrix that multiplies a vector and then produces another vector. Now what is this 10 element vector or a 100 element vector? The 100 element vector is a point in 100 dimensional space. And the 1 element vector is, just is one data point. Let's say for to bring more complexity, let's say the output side is a 5 element vector. So you're turning a point in 100 dimensional space into a point in 5 dimensional space. And that can be done by a matrix. And the entire task of machine learning is given enough data to learn that matrix. If it is one, you can have multiple matrices, so you can have layers of matrices. But that's what's happening. You're literally just turning a vector into another vector by using internal matrix manipulations.
Right. And these ideas you explain in a lot of detail in the book, step by step, with a lot of diagrams and explanations, so on. What were you expecting people who are reading this book and who may or may not have a bit of math background? What's the best way to engage in the book, not lose interest? And you have plenty of stories to make sure people don't, but still, math can also become daunting. What is your advice to people who really genuinely want to know? I really want to understand, how neural networks work, and maybe using your book as a guide. So what's your advice of how they should?
So one of the things that a writer of a book like this relies on is some inherent curiosity in the reader, right? The reader is curious. So they are, I make no bones about it. Like you say, in the prologue itself, I say, this is not bedtime reading, right? It takes, you have to persist with it. And I completely understand that math can be daunting. And, and I know that when I got into learning the math, in the beginning, it did feel like that. But what was interesting was that as you encounter more and more of these ideas, just like neural networks learn from data, our neural networks also start seeing patterns in the information that you're coming across. So if you're truly genuinely curious and you want to learn, first accept the fact that this is not trivial, right? That it's going to take effort. And if you just kind of set yourself up saying this is fun, but also hard, but not so hard that it's impossible. And then you take bite-sized, pieces of information, and somewhere it starts coalescing. And the whole effort at telling it through stories was exactly that, to not completely overwhelm the reader with the math, but yet the math is the point, right? And so the stories are in subservience to the math. And the hope is that the stories keep the reader engaged, but the math is where they spend more time.
Yeah. And from my perspective also, I'd like to share with the readers that AI is here to stay, is going to increasingly play bigger and bigger role in our lives. We will all end up being users of AI. There's no question about it. But by engaging a book like this and indulging some of the curiosity and maybe putting some effort, if you're able to get some glimpse into what's happening under the hood, your appreciation for the technology and the confidence also, is of different kind.
Yes.
So it's probably well worth the effort, because this is something one would live with for decades. And even if you're able to have some glimpse on how is this a tiny baby neural network is able to recognize the letter C from letter J, that teaches something about this. From there on, just extrapolation and scaling. But you get the essential gist of what's
Yes.
going on.
No, I completely agree. I'm glad you see it also like that, because for me, that's exactly that there is something amazing. There's a transformation that's happening to society, and we are fortunate or unfortunate to be caught in the midst of it. We are literally in the midst of it.
Time will tell.
Time will tell, yes.
Yeah.
So, but if you just look at it as a intellectual thing that humans are doing, this is after all a human endeavor, right? It's not coming from anywhere else. This is us figuring this out. We have built this. And just like anything else, the steam engine or the internet, or doesn't matter what it is, it's a human endeavor. This is just like that, except its potential to transform our society is probably far greater than anything else that has come before, because the speed at which it is going to happen, the scale at which it's going to happen, and how pervasive it's going to be. So bringing that curiosity to those of us who are even a little bit mathematically inclined, right? Because this is not, like you said, this is not hard math. And I really do think dwelling on the beauty of the math helps.
Yeah.
Because if you get excited about, vectors, I remember doing vectors in college and being completely bored because the context was never clear, right? But now suddenly the idea that, hey, vectors are probably how our brains are also doing what they're doing, right? That changes things because, and then you see these machines doing what they do, and it's just manipulation of, vectors and matrices. The fact that you can get this incredible behavior, you can sit in front of ChatGPT and ask it, you give it an entire document in English and say, summarize this in Hindi for me, and it does it.
Yeah.
And to realize that underneath all of that, it's just vectors and matrices being manipulated.
Yeah.
That to me is mind-blowing, right? And to appreciate it for that would be amazing.
Yeah, absolutely. I hope a lot of people get inspired, pick up your book, and both enjoy the story as well as, persevere through a bit of math. I think the payoff is really going to worth it. Just my last question, I think there is a huge interplay both in past and perhaps in future in how our brains work versus how these neural networks are working. The fact that we call these things neuron is obviously, came from how our understanding of, we do have neurons, the actual biological entities, and it's a big complex web of networks. And we know from, most of learning is adjustment of those weights. I think that's pretty much our best understanding how learning happens in the brain. So do you see this back and forth? And, do you also hope that as we get much better with this technology, we learn something more about the brain in the process, and, the more we learn our brain, we'll be able to take more ideas back to how we're building these things?
Very much so. I think, and you have to keep this in mind, right? That a lot of the researchers who are working in AI are also interested in the flip side of trying to use AI to make sense of the brain. So some of the computational models we had of how brains work before deep neural networks, they have now been supplanted with, deep learning models of the brain. And these models are turning out to be much better at explaining certain aspects of the brain than the previous models were. So obviously we are getting closer to making sense of, what the brain does. But we also have to be sort of slightly cautionary about this, that like you said, we talk of artificial neurons, but these artificial neurons are extremely simplistic models of what a biological neuron is. There have been papers that have suggested that even a single neuron, like a complex single neuron in the cortex, you might need to model it with an entire multi-layer network. So we are very, very far from duplicating the complexity of biological neurons in the artificial systems. But this is a two-way street. There is a whole field called neuro AI now, another buzzword that has come up, but that's trying to work at the interface of AI and neuroscience. So certainly ideas, modeling brain behavior using deep neural networks is helping us understand the brain. But there are things that we understand about how neurons work, about how our brains work, that's also having an effect in the other direction. For example, one of the big concerns about all of these LLMs is the energy consumption. The incredible amounts of energy that goes into training. Our brains, on the other hand, which are incredibly more capable, are working off 20 watts or something, right? So, and one of the reasons, amongst the many, but one of the key reasons why our brains are so efficient is because the neurons, they are what are called spiking neurons. So if you look at an artificial neuron, if you were to implement the artificial neuron in hardware, not in software, but if you turn that into a hardware neuron, it would be the equivalent of having its output always on, right? So it has some output, but it will be a voltage signal that's constantly on, whether it's 1 volt or 2 volts or 3 volts. So it's constantly consuming power. Whereas if you look at biological neurons, they communicate with each other using spikes of voltages. And they're mostly silent. If you look at any individual neuron in an ensemble of biological neurons, it's usually just not doing anything. And then occasionally it will fire. So it's very, very efficient in how it communicates with its neighboring neurons. So those ideas are now being used to build artificial spiking neurons and potentially build them in hardware that would become much more like 2 orders of magnitude more energy efficient than what we have now. So it's a two-way street. And the hope is that for a lot of researchers, the hope is that by building these systems, we understand ourselves and our brains.
Yeah, and that makes, what's happening is even more exciting, while I think things that happen around us and how we live, work is going to change. But there is massive amount of investment is happening in this area. And perhaps, maybe we'll end up building some kind of AGI, which will be interesting in its own way, but also maybe learning something about our own brains in the process. So all that is super exciting, good or bad, time will tell. But I want to thank you, Anil, for writing such an accessible book for such an important topic. I think it's, anyone who's interested in AI will do well to, I think, spend some time with the book and develop a deeper understanding and maybe get inspired to learn more. And you've spent last few years to go really deep in this area, and maybe this book can also act as a catalyst for people to learn more about this very important area. Thank you.
Well, thank you very much for those kind words. Thank you.
At SparX, we aim to bring to you stories of exponential impact. We share in-depth analysis of what goes behind success stories. If you find our conversations interesting, you can join us by subscribing to our YouTube channel. You can also listen to SparX on Spotify, Apple Podcast, or any other audio platform of your choice. If you have any suggestions on who we should invite or what topics we need to cover, just let us know in the comments. We are always listening, looking for ways to improve, and keep getting better as we go along.